Okay, good morning again. Today I like to start maybe with the BJT transistor concept because we need to know about multi-emitter BJT because that's what we will be using in the coming slides. As you know, for the BJT, we keep saying that, this is how we implement the BJT. We have N plus region here, and then P region here, and N region here. And then we call this side as the collector, this side as the base, and then this side as the emitter. So, in normal operation, we have this junction on. So it's forward active, and then, forward biased. And then electrons, go here, whatever. And then we have reverse bias junction here. And then, any electron that's coming here is swept through the collector. So electron will move from any electron here will move from here to collector. That means current is in this direction. Okay, so this is the basic thing. We learned about it, so we call this thing collector current. And then this current is going to be emitter current, and then or this capital, and then this current is the any current that's coming from here. That's called the base current. Sorry, base current is direction is wrong, I guess. Current is in this direction, so I base current. Okay, so we show this two-dimensional view, and sometimes we say that in normal cases, in fact, maybe we can do this. Sometimes they show it this way. So this is going to be the device. So N plus P and then N here. Okay, so again, we call this side collector, this side base, and this side is emitter. Okay, but in IC technology, this is not what you do. This is just the concept, but in the fabrication of the IC, we take this silicon wafer. Okay, so this is the silicon wafer, and this is the cross-sectional view. Maybe here. Okay, so we have okay, so this is the wafer thickness, about maybe 700 micron. Okay, depending on the diameter of the wafer. If it is larger diameter, we make this thicker so that it doesn't break naturally. But here we form the transistor. Maybe I'm going to do this and then draw it again. So typically we take a wafer, and then this wafer has two maybe doping regions, and we call this thing, this is silicon. It can be N-doped or P-doped. Let's say this is P silicon. Okay, P-type silicon. This is substrate. And then on top of the substrate, maybe a certain thickness is formed, and then maybe 10 micron or so. You will see this as the N-type silicon. So that means it's phosphorus doped. And here, what we do is we need to create this transistor, emitter, collector, and base. And in order to do that, let me try to select some maybe colors here. We let's say dope the I mean, well, for one thing, we dope the device like this with the P++, so highly doped. And then we dope, let's say, this region, highly doped P++. And then we dope this region, let's say P+, maybe a different color, maybe this one. Okay. Okay. So this is P-doped silicon. And then, you know, that's lightly doped. So the other one goes all the way in here. This one maybe is going to be, I don't know, 5 micron or so, let's say. Okay. And then we, I mean, this region again is N-doped and silicon. And then we dope, let's say, inside with N+. So we make here, let's say, N+. Okay. So when we have N+ here, that's going to be our, in fact, emitter. Okay. So this substrate, I mean, we need to contact to the substrate. We also do N+ here. And this becomes our collector. And here, we take a contact to P+ substrate by doing doping. Let's say this one. And then this will be P+. Okay. So shallower P+. And this becomes our base. So the device indeed is formed here. So you have here emitter, base, and collector. So this is N, this is P, this is N. Okay, so the device is a vertical device. Is that clear? Let me take this a little bit down.
Hocam sağda soldaki B++'lar ne işe yarıyor? Onlar niye var?
Those are for isolating different BJTs from each other. Okay, so you know, if you look from the top view, we have this region, P++. So now we are looking at the silicon from top view, okay? So this one is creating an island so that, you know, you can put maybe another BJT here. Okay, BJT1 and BJT2. Oops. Okay, so you form transistor 1 here, transistor 1, and then this is going to be transistor 2. Okay, because you want to isolate the collectors, and then here you apply this is the common, and you want this junction to be turned off all the time. So how can we achieve that? P++ needs to be connected to the lowest voltage in the system. Okay, so maybe 0 volts. Okay, smallest voltage. Therefore, you make sure that this junction is always off. Is that clear?
Yes.
Okay. So the main point here is that the device, in fact, is formed vertically. I mean, in this device settings here. Okay. So and this one is collector, this one is base, and this one is emitter. And that's how it's formed. You know, why do we put this N+ here? Because getting a good contact here is important. And in order to get a good contact here, we need to put metal here. Okay, metal and metal. So these are maybe aluminum. Metal contact. And then in order to get a good contact here, as a ohmic contact, you need to have N+ here. So N+ makes a connection here, and then you have the current coming all the way here, and then now that's going to be your device. But you know, this is lightly doped, this region, and therefore the collector resistance is typically not that small. So they do trick here. This is typically substrate. The substrate is what we call single crystal silicon. Oh gosh, my spelling. Single crystal. How do we write? Oh my God, I forgot. Anyway, something like this, I guess. single crystal silicon. Okay, so but this one is epitaxially grown epi silicon. So therefore, on top of P single crystal silicon, we can have N type single crystal silicon. But in order to get a good, maybe reduced resistance in there, typically people maybe do doping here, and therefore this doping I'm not still very comfortable here. So you can put here again N plus doped region, and therefore the current, when you try to follow the current will go from here, maybe some resistance, very small resistance, and the current is going to go all the way up here, and then collector, emitter, base and emitter. Okay, so there's a buried N plus layer reduces the resistance, collector resistance. Okay, and from the base to here, there is already resistance here, so this is going to be R base. This resistance that you see here all the way is going to be R collector. Is that clear? This is how we implement. I'm sure you have a lot of questions here. So in the modeling, or in the small signal model, we see those resistances. In large signal model, it's not that those critical, but in fact, your transistor is going to be having these kind of resistances, RB and RC. But thanks to that buried N plus doped layer, that collector resistance becomes small. Okay, so the reason for this, maybe we should also write here, to obtain ohmic, sorry, I lost my spelling today, ohmic contact. Okay, I mean, if you have maybe we should have talked about this in the past, but in order to get a good contact for a PN junction diode, this is, I mean, if you have, let's say, a PN junction, okay, so this is P and this is N. If you put metal here to get a contact, metal, and then metal here, you get a contact. But this metal, in order to get a good contact to this, we typically put here first P plus, and then here N plus, okay? Otherwise, we don't get a good ohmic contact. So, you know, in the PN junction, I mean, if you look at this region here, you know, the current between metal and the resistance between metal and P plus is very small. And then if you look at the IV curve, and this is going to be very sharp here, the IV curve. Okay. And then 1 over slope, 1 over R is going to be our contact. This is our contact. I mean, first of all, it will be resistance. The second thing is that this whole thing is 1 over conductance. So slope is very large. If P plus, then our contact is very small. Is that clear? What happens if we do this? Let's say we have N dop region, lightly, and then metal. Then the resistance between N type and then metal here, you will have here Schottky contact, Schottky barrier. There's going to be Schottky barrier. Basically here, the IV curve is going to be like this. The I and then V, and the curve is going to be something like this, you know. And here, if you notice this one, this will look like a diode actually. And the voltage, turn on voltage is going to be 0.3 volt or so. But it will be both sides, minus 0.3 volts. Okay. So we call this thing, in fact, this whole thing, we call it Schottky barrier diode, actually. Okay, so in order to prevent that Schottky barrier diode forming, we put here this one. Okay, so obtain to obtain ohmic contact, we put here N plus. Is that clear?
Yes.
Okay. I hope it's not too much confusing. I'm sure it is a little bit confusing, but I hope it's not too much. So, I mean, the point here is that the BJT we talk about is not a device like this. It's not a device like this. It is what you see here. Okay. So now I explained the Schottky contact concept so that at least you understand what is an ohmic contact and then how we achieve it with M+ or P+ regions. But we will be using this Schottky contact sometimes to our advantage. And, you know, you will be seeing that. Is the BJT okay now? I mean, now, some people, this is the standard BJT. If we want to make multi-emitter BJT, sometimes that's what we will need. So we will take this, okay, and maybe this, and this one. Okay, so this is maybe, so here is P++ region, and then we contact here 0 volts, and then this is to separate the next transistor. So we do doping here, P++, and this is P substrate. So P doped substrate. I mean, that means P doped silicon. And that's also lightly doped. And then, what was the color that we selected here? I guess we selected this color. So now I'll do something weird. Maybe this. Maybe even larger. Okay, and then we doped inside. Now I'll do this. Doping here, P+. And then we need to do N+ here. Oops, maybe not there. A little bit here. N+. This is N epitaxially grown silicon, N episilicon. Okay. Now I'll draw maybe a little bit more actual drawing here, and then in the layout we can draw this N+, N+, and N+, more than once. Okay, so let me do this also. Typically we make first here silicon dioxide isolations. This is more realistic drawing. Okay, so this is silicon dioxide. So silicon dioxide, that's an isolator. And then here we put everywhere metal first. Maybe I should have done this also. Silicon dioxide. And then we put everywhere metal, and then etch metal from other regions. So this is going to be metal. This will be metal. This will be metal. This will be metal. And interestingly, we do this. I will explain what this is in a couple of minutes. Okay. So these are metal, typically aluminum. And then it gives us, good contact here, ohmic contact. And this region is called emitter. This is also emitter. This is also emitter. This will be base. This will be collector. And this region, again, will be ground, lowest voltage. So we will call this thing emitter 1, emitter 2, and emitter 3. So we can obtain multi-emitter device here. Multi-emitter device. This region is N-doped. Sorry, P-doped. So we formed a new type of transistor here. Collector, base, multi-emitter device. Emitter 1, emitter 2, and emitter 3. Okay. You can consider this to be, let's say, a device like this. They have common emitters, or sorry, common collector. And the base is touching here, and touching here. This is the common base. And this is emitter 1, emitter 2, and emitter 3. We are recording, right? Yeah, looks like we are. It's good. Okay. So this type of 3 transistor will be useful for us to make maybe NAND gates. Okay, NAND gate inputs. We obtain NOR gates, but this will be useful for NAND gates. So I don't know if you remember DTL. In DTL, in order to make a NAND gate, did we do NAND gate in DTL? I don't remember that. This was the DTL, remember? RB, RC, and QO, DI, AVDL. So this was inverter. But in order to get NAND gate in DTL, you could do this. Okay, so this would be A input, B input, and C input. This would be VCC, and then DLQ. So let's just do it two of them, maybe. I mean, maybe three is a little bit more than what we need right now. So if you do this, this will act like a NAND gate. What does that mean? If any of them is low, this is Vx. Any low, output will be high. Any input low, then Vx is equal to 0. Let's say 7 volts. And when we say low, let's say 0 volt. 0.7 is not enough, so QO off. So then Vout is high, or CRB. Therefore, Vout is high. Okay. So all inputs high, then Vx is 1.6 volts, or sorry, 1.5 volts, because this will be on. And then Q is SAT, QO, therefore Vout low. Okay, so that's an AND gate. So we can obtain a NAND gate also in the in this device. This was RD maybe. This is QO. And this device goes to here. RCP. Okay, so QS and then QI. Okay, so if let's make a table, A input and B inputs. Okay, what is QI? What is QS? What is QO? What is output? Okay, we can also sign CP DL. So if any one of them is 0 volt, let's say 0 volt, this is also 0 volt. And what is the state of QI?
Saturation should be.
It should be in saturation. Okay. If QI is in saturation, this voltage is, if let's say this is 0 volt, then this is going to be 0.2 volt. Then QS will be off, QO will be off, V out will be 3.6 volt. Okay, because QCP is what? Edge of SAT, edge of conduction. DL, edge of conduction. Okay, so if one of them is 0, but the other one is, let's say, 5 volt. What is the transistor state?
Saturation.
Saturation.
Still saturation, right? Because think about that. There's a diode here, and there's a diode here. So this diode is going to be on. This diode is going to be off. For which case? The 0,5 case. Okay. So therefore, if one of them is on, then this junction is going to be for sure off. This will be off. Why? Because it cannot turn on. Sorry. What am I saying? I'm saying something wrong. We say SAT, so it should be also on. But you know, no current is going to be able to pass through here. No current, so no current here. This current is going to be I collector of I, again, is going to be 0, so it will be in SAT. So this will be also in SAT. Once that one is SAT, this will be off, this will be off, this will be 3.6 volt again. So the other case, let's say, is this case, 5 volt to 0 volt. This will be still SAT, off, 3.6. Okay. So if you look at this transistor, you know, one of them is on, is enough to pull the base to 0.8 volt. Okay. So anyone on any of, maybe I shouldn't write here because it's just a transistor. So we are talking about the BJT here used in this structure. So if the all of the junctions are off, so if we have 5 volt here and 5 volt here, then the transistor will be this junction will be on, but these are going to be off later on. So this is going to be in reverse active. And if it is reverse active, QS will be in SAT. This will be in SAT. Output is going to be 0.2 volt. Does it make sense?
Yes.
Okay. So just by adding one more diffusion region, we are able to implement NAND gate or multi-emitter BJT. So this is called multi-emitter BJT. That's it. So here, you know, I added one more concept here. If this is fine, I'm going to go to the next concept. But maybe we should give a break here on time and then come back for the next idea. Okay. This is therefore TTL NAND gate. Okay. We have seen NOR gate. We have seen the TTL NOR gate before. But it's very easy to make TTL NAND gate. Okay. So this is NAND gate A, B, and Z. Okay. Let's give a break. Okay, so any questions here? If not, I'll go to the next idea and concept here. You know, we did something here. This point. What was this point? Why did we do this? You know what we did? There was between base and collector. In fact, we have this creates Schottky barrier diode. So that means between base and collector, okay. So Schottky barrier diode between base and collector. So for our, let's say, this is not multi-emitter, just to simplify things here. We have here a diode, but this diode is, you know, we show this one is in this case like that. So V Schottky barrier diode, I Schottky barrier diode, So that diode has a response curve like this. And this point is 0.3 volts. This one is minus 0.3 volts. So it's not an ohmic contact. It is a Schottky barrier contact. It is as if it is a diode. So this, the model is shown like this. So we call this thing V, Schottky barrier diode, and then this one is current I, Schottky barrier diode. Okay. So and this is our transistor, BJT transistor, and then something between collector, base, and emitter. You have this coming in parallel. So that element, in fact, prevents this one, prevents base collector junction to turn on. Okay, so that means it prevents the BJT to go to SAT. You know, what was the problem with this saturation? You know, when it goes to SAT, that base charge was large, and then we had to remove that base charge. Okay. The problem with BJT going into SAT is that the base charges, the minority carriers in there, you know, when it's in saturation, the base charge needs, base charge is high, and it needs to be removed quickly to put the transistor BJT to the cutoff mode. Okay, so but you know, when the base collector junction is high, you know, in this you know, turn on here, and base to collector is in SAT, so it takes time to remove that. However, here we have already a diode here, and then there's a diode coming in parallel. So the device in there, the transistor, so Schottky barrier diode turns on before base collector junction. Okay, turns on. So base collector junction cannot turn on. So that's strange. So what happens then? If we think about this as a device. If we have a device like that, let's say this is V in, and then we are using this in RTL, VCC, okay? And then here is the diode we talk about, V out, RC and RB, okay? So when V in, V in is equal to 0, then, you know, this QO, and let's say these Schottky barrier diodes are both off. Maybe that Schottky barrier diode is going to turn on or off. It should be off also. Anyway, QO is off. So, but when V in is equal to 5 volts, this junction, so when this is 5 volts, this junction turns on and this becomes 0.8 volts because it's a lot of current is coming. And then this turns on and this becomes 0.3 volts. Therefore, V out becomes 0.5 volts. So low, but transistor Q is, we call it, I don't know, there's a name for it, but it is not in SAT. It's a different, you know, we call it QO is in hard on or something like that, you know. So when Vin becomes 0 volt again, Q becomes off very quickly because no minority charges involved. Okay. So this is merged. And doing this is very easy in the process. You see, it's very easy. You just, you know, extend this region, and that's it. That comes naturally. I mean, it might be one contact or multi-contact or multi-emitter, one emitter. So this device or this element is shown like this. Okay, they merge it. Schottky barrier BJT. Schottky barrier diode BJT or something like that. You know, that's the name. Okay. So this is,
Hocam,
yes.
how come VB junction is 0.8 volt? Because the transistor isn't forward active.
You know, for this case to happen, there is a huge current going here. So when there's a huge current in here, so transistor is in hard on, you know, they measured the base emitter voltage, and after the measurement, they find that it's closer to 0.8 volts. So, and then we say it's 0.8 volt. Is that okay?
Yes.
So that's a special case of the transistor. So, I mean, the transistor shape even changed. So then, you know, this type of transistor is used so anytime a transistor can go into saturation, then we select that transistor to be Schottky barrier transistor. It's so simple, you know, in the implementation to make it. So when we look at our TTL, we out. So we select this transistor to be Schottky barrier, this transistor to be Schottky barrier transistor, and of course we have this, let's say RD. And even this transistor is not selected to be, you know, probably not. Maybe yes, I don't know. Okay. But this one, no need, because it never goes to saturation, typically, so no need to be put it that way. So this is called Schottky TTL. Okay, or STTL. So as you see, I mean, if you look at the data sheets, you can compare the data sheets of standard TTL and STTL. If you do, to observe the switching times. Okay, to observe the switching times, and then you know, T switching of STTL is much faster with very simple, you know, trick. That's what is obtained. Of course, you know, this means maybe output voltage is not 0.2. The output low is 0.5 volt instead of 0.2 volt, but it's okay. Okay. So I mean, when you see STTL, we explain this so that you understand what it is and then what is the advantage of it. And this is, you know, VA, VB, and VC. So multi-emitter, you know what it is and why, you know, we have this and what is the advantage of it. Okay, but we won't spend you know, too much time on this. But you know, there are low power Schottky TTL, you know, high speed Schottky TTL. You know, when you say low power Schottky TTL, they increase these resistances so that the power consumption is going to be small. You know, so there are high speed ones. That means, you know, they decrease those resistances, so the power dissipation is high, but the switching on and off is faster because there are more current available for charging and, you know, discharging the capacitances, parasitic capacitances or line capacitances, the PCB capacitance, you know, PCB line capacitances. Is that clear? So this was extra explanation before we go to our course slides. So I will go to course slides and then continue if you don't have any question. If you have questions, please let me know. You might need to watch this one more time, maybe. Is that okay? So Damas and Sicconi, the book, explains, you know, the other versions of TTLs in depth, and for each of them it gives you voltage transfer functions and other things. But we will not be, you know, spending more time on this. It's just, but we thought that it's important, you know, to at least mention about it in the course. Okay, now that we understand what this element is, the QI, we will show you one other topology and one other trick that we add. You know, for the inverters, we typically have an enable, you know, input also. So the enable input is going to give us an element as if we have, let's say this enable with the inverter is going to be, you know, effectively acting like this. Let's say this is A, this gives us A bar, and then this is Z output. Okay. So, and this is enable. When enable is high, enable is logic 1, okay, this will be on, so it will be turning on. Enable on means Z is equal to A bar. So the interesting thing is when enable is 0, then Z is going to be floating. or high impedance. So it is not pulling it down or it's not pulling it up. So voltage is not either 0.2 or 0.5. We don't know, I mean, what it is. Okay, such an element is a very useful element. You know, when we say buffer, buffer is like, you know, two inverters back to back becomes buffer. Okay. So this is a very useful element. In fact, you can do, you know, what you can do. What can you do with this? You can use this as a multiplexer. Such an element. So here, the A, let's say this element, how does it work? This is A, and then we have a switch here. Okay, and then the other one, the B, when you say bubble here, that means enable bar is entering. Okay, so this is going to be such an element. So I guess this inverter thing is missing here. But maybe I shouldn't put an inverter here. So let's make this thing without inverter. Let's do this. Okay, so this will be the device. So here, when we have enable, when we connect enable here, okay, this is B. So Z is going to be determined by enable. If enable is high or logic 1, then Z will be equal to A. A will be connected to Z. Okay. So enable low, that means logic 0 is applied, then Z is going to be B. Why? Because when enable is low, this one is going to be on. So let me explain this here. The switch, this is when you apply 0 volt here, the switch is off. When you apply 1, logic 1, maybe I shouldn't say 0 volt, but 0. 0 here. That's the connection. Okay, that's the device, how it works. And if we have bubble, then the bubble when this is 1, this will be open. And then if you have bubble, logic 0, this will be on, touching. So here is logic 0. Okay. And that's how it works, the switches, in terms of, at least, you know, conceptually, that's what it is. Okay. So if, let's select some colors and then do this here. Let's say enable is high. If enable is high, this will be connected here, and the output of this is called high impedance, high Z. So the value in the resistance here is determined by this A output. So the Z will be equal to A. Okay, for the other case, let's say enable is low. Maybe I should say low here, or 0. So high means it's 5 volt maybe. Okay. Then if that's the case, then this is going to be Z will be equal to B, and this will be high impedance. So I mean, the output will be determined by the B input. Okay, so this is a very useful device. And then, you know, in electronics, this is used for the buses. Let's say in a memory element, right? You know, like let's say you have memory. Okay, 16-bit memory. For each bit, this is the bus, common bus. So this is the elements, many memory elements, okay? Which one, they are all connected here, but only one of them, you know, if you select this memory element, then this determines the bus, and then that information is transferred into arithmetic logic unit. I guess you'll learn about these concepts maybe in 348. Okay, so in summary, there is such an element, and then we can, you know, make that element, and, you know, for the target of this course is to teach you how to implement such circuit elements, like NAND gate. How can we implement NAND in TTL? How can we implement NOR? How can we implement enable into such gates? And that's one of the ways, for example. So is the general idea clear? No answer, no answer. Hey, come on, is it clear?
Yes, it's clear.
Clear hocam.
Okay, good. So now I will show you how to implement this. Okay, so just one step further than inverter. I mean, if we didn't have multiple emitters here, it will be just an inverter, right? I mean, if I connect A to B, it will be an inverter with enable. So Now, we can check the function of this element. So first, we will look at what is happening if, let's say this enable, okay. I'll make a table. I'll make a table and then say what happens to A, B, enable inputs, and then the state of the transistors, QI. I mean, I can make a very big table, you know, showing every element, the state of every element. I don't have space here. I mean, maybe it would be better, but is it? Maybe next page can be useful for this. Yeah. You know, next page, or before going to the next page, that's showing enable high. What is the state of enable high? So let's check enable high case. You know, we can give different conditions here: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Okay, for these cases, we want to find what is going to be happening. So if the enable is high, what happens? So maybe I can draw state of the transistors. Okay. I don't need A and B. In fact, before A and B, I'm going to write the state of the enable. And then let's say this, what is QI? What is QI? What is QS? What is QP? What about DL? QP and DL. And then what is QO? Okay. And then maybe I can say this one is Q4. Let's say this is 5. And this is Q6. Okay. So Q5, no, Q4, sorry, Q4, Q5, and Q6. Okay. So when enable is high, this one is, let's say, 1. Okay, we don't care about this one. No, sorry. So I'm looking from a different perspective now. Maybe I shouldn't have done this. it would be better to put the enable to first column. Okay, I'm switching my concept here. This is A, this is B, and this one is enable. And then I started with the other way around, enable 1. Okay, so this is the case now. When enable is 1, let's look at this one now. Enable is 1. What is the state of this transistor? So if we have 5 volt here, what is Q4? This junction is
Off.
on. This junction is off. No. There's 5 volt here. 5 volt here.
Reverse active.
This is going to be reverse active, okay? So when this is reverse active, what is the state of Q5? It will be in SAT. When this is SAT, what is the output voltage here?
0.2.
If it is 0.2, what is Q6?
Off.
Okay. So this is not affecting anything. Remember, enable is high, is in the multi-emitter world, you know, N plus, N plus, and N plus. Emitter 1, emitter 2, and emitter 3. I mean, if one of them is, this is P plus, and this is P, one of them is high, means this is reverse off. Okay. So if the junction is off, BJT state is determined by the other transistor, by the other inputs. Okay. So in fact, here we say this is reverse active, this one is SAT, and this one is off. Okay, so this will be the case for all of them. Okay, but for this case, let's say this one is A is 0. So what is the state of this QI? Let's say this is the case, 0, 0 case. For 0, 0 case, QI is in, this is 0, this is 0. QI is in
Saturation.
saturation. Okay. If that one is saturation, this is going to be off. And then this will be also off. And output is going to be, sorry, QP. QP is going to be not off. This will be on. This is going to be edge of conduction. Okay. So therefore, output is going to be high. Okay, there's no space for that, but output is high. Okay, no space for that. So for the other case, still this is going to be sat of edge of conduction. I made a mistake here, I guess. This is going to be off also. Okay. This is going to be also off. This will be the same. Okay. Here, if inputs are both, all of them are, let's say, high. Okay, high and high. Then the QI will be reverse active. If that's reverse active, QS will be in SAT. This will be in SAT. These are going to be in off. Both of them. Okay, so output is going to be low. Okay, so here, maybe I can write here V out. V out is going to be low here. In other cases, they will be high. High, high. Okay. So therefore, this will be acting like, you know, when you have this one with the enable high, this is as if you have a standard operating NAND, okay? Normal. Okay, so the interesting thing happens if we have you know, Z or enable to be 0. If enable is 0, A and B, so let's say this is Q4, Q5, Q6, okay? And then we can look at QO and we can look at QP and DL. So if this one is 0, let's not just, you know, don't care here. Q4, Q5, and Q6. Q4 will be what?
Saturation.
Yes. So this will be in SAT. What about Q5?
It should be off.
Yes. Q6?
Saturation.
Yeah, it should be in saturation. Okay. So if this is in saturation, the voltage here is going to be 0.2 volts. Okay, so this will be SAT, this will be off, this will be SAT. So this voltage is going to be 0.2 volts. It's forced to be. So when enable is 0, what is the state of QI? We don't care about the other inputs. If one of the emitters is 0, then it pulls this node to 0.8, and this is becomes 0.2. So this is SAT. Okay, so this will be 0.2 volt. And this will be off. This will be off. So 0.2 cannot turn on both QP and DL. So this will be off.
Hocam sesiniz gelmiyor sanırım.